Today we have Dr. Wil Burns joining our Rutgers Energy Institute's Energy Policy Seminar Series. He's going to be presenting on scrubbing the skies, carbon dioxide removal approaches, and their potential role in addressing climate change. Dr. Burns is the co-executive director of the Institute for Carbon Removal Law and Policy at American University. He is also a visiting professor of Environmental Policy and Culture program at Northwestern University. He holds a PhD in international law from the University of Wales, Cardiff School of Law. And with that, I turn it over to Dr. Burns.
Thank you so much, Kevin, for the invitation, and thank you everyone for attending today. So I'll jump right into this. As you all know, the Paris Climate Agreement, which entered into force in 2016, establishes the salutary goal of trying to hold temperatures to well below 2 degrees Celsius and at least aspirationally to 1.5 degrees Celsius. However, if you look at the tepid nationally determined contributions or pledges that countries have made to date, it puts us on track not for meeting that goal, but indeed probably temperature increases of somewhere between 3.2 and 3.5 degrees Celsius by the end of the century, with temperatures continuing to increase for centuries beyond, given the inertia of the climate system. And we also know that temperature increases of this magnitude could prove disastrous in terms of human institutions as well as ecosystems. For example, a 3 degrees Celsius increase in temperatures could completely melt the Greenland ice sheet, and that alone could raise sea level by more than 20 feet over the course of the next 1,000 years. Virtually all coral reefs could disappear under a temperature increase scenario of 3 degrees Celsius. 3 to 4 degree increase in temperatures could threaten 60% of the world's species, ultimately with extinction. It could also result in catastrophic declines in agricultural production, especially in some of the most vulnerable countries in the global south. And as a consequence of this, there's increasing recognition that large-scale deployment of so-called carbon dioxide removal approaches may have to play a critical role in helping us avoid passing critical climatic thresholds. And I have a working definition here, right? So these are options that remove carbon dioxide from the atmosphere and sequester, meaning store that carbon dioxide in terrestrial systems or in ocean systems, or utilize it for things such as fuels production or materials or carbonated beverages, for example, as a way to reduce radiative forcing in the atmosphere. Indeed, in the Intergovernmental Panel on Climate Change's fifth assessment report, of the 208 integrated assessment models that were able to effectuate holding temperatures below 2 degrees Celsius, 184 of them contemplated large-scale use of carbon dioxide removal in addition to aggressive decarbonization to achieve the goals of the Paris Agreement. Indeed, when we look at estimates of how much carbon sequestration may be required, recent estimates are that we will have to remove somewhere between 13 to 20 gigatons of carbon dioxide equivalent every year by the year 2100 if we're to hold temperatures below 2 degrees Celsius. Moreover, many studies see a critical role for carbon dioxide removal should society overshoot its temperature targets, meaning we exceed 2 degrees Celsius and we would need carbon dioxide removal to help us decrease our temperatures below that threshold in the longer term. So given this increasing exigency for CDR, I thought I'd seek to provide you with an overview of these technologies. And we'll look at two things in this presentation. First of all, I'm going to look at a series of potential carbon dioxide removal, also often called negative emissions technology options, on the axes of potential benefits, challenges in deployment, as well as some of the potential risks associated with these technologies, especially at large scale. And then second of all, talk a bit about the governance options, both at the international level and the national level for wide-scale deployment of these technologies. So let's start off with looking at some examples of these approaches. The first of these that we look at is large-scale afforestation and reforestation, tree planting. As we know, trees take up carbon dioxide to utilize them in the photosynthetic process. And so there's been proposals to plant large amounts of trees, including the Trillion Trees initiative at the international level, and some discussion of that in terms of US legislation also. Now, in terms of the potential of this approach, one thing that's striking is that estimates vary widely, largely based on sustainability considerations. So some studies indicate that ultimately we're probably only going to be able to sequester about a gigaton of carbon dioxide annually with this approach, while other studies indicate that afforestation and reforestation could provide up to 30% of the sequestration that is necessary to meet the Paris Agreement's objectives. But there are also lots of questions associated with the effectiveness of this approach. One is the question of permanence. If you plant substantial amounts of trees and climate change ultimately results in a massive increase in temperatures that results in the burning of a lot of these trees, you're going to lose those carbon benefits very quickly. And powerful attestation of that is in terms of what we've seen recently in Australia and California, and in some projects that have specifically planted trees to sequester carbon, where most of the trees have disappeared as a result of increasing forest fires. We also worry about maintaining those trees. One of the things that's critical is having the resources to continue to protect those trees and to ensure that they thrive. Those kind of resources, including extension services, for example, are not always available. For example, in one recent study of a tree planting project in Chile to effectuate carbon sequestration, the study indicated that 75% of those trees were gone within 2 years. And this was primarily because of inadequate resources to continue to protect those trees. Another thing that we worry about is where those trees are planted. If trees are planted in the northern hemisphere, especially in boreal regions, you may see that most of the climatic benefits of increased sequestration, or all of those benefits, are obviated by the fact that you are decreasing surface albedo, the reflectivity of incoming solar radiation. So as a consequence, more solar radiation would be absorbed in those regions, and that would offset the benefits of the carbon sequestration. Why this is important is when we look at some of the proposals for planting 1 trillion trees, for example, most of those studies assume that at least 20% of that tree planting will occur in ice-based areas. And if that happens, the science may be ignored. But the bottom line is that you may not see any benefits in terms of climate change. And so that's another issue that has to be discussed. Additionally, there are social justice and environmental concerns associated with large-scale tree planting. One recent study talked about potential exclusion of people from lands that are critical for livelihoods by elites to obtain carbon credits or to meet NDCs. And indeed, in the REDD+ program, we've seen a number of these kind of expulsions occur, and that's at a much smaller scale than what would be necessary in this case. And indeed, studies indicate that the easiest and the cheapest areas to effectuate these kind of tree planting programs may be in failed states where elites are perfectly amenable to these kind of land grabs and expulsions. Moreover, some studies indicate that a lot of these trees would be planted in grassland and savanna areas, especially in the global south. If this were to be done, it could have massive negative impacts in terms of biodiversity, given how rich these kind of regions are. And as a consequence, one recent study indicated that it would have as much negative impact in terms of biodiversity as most of the business as usual scenarios in terms of climate change. All right, so that's afforestation and reforestation. We now move to bioenergy with carbon capture and storage, or BECCS. So the way BECCS works is it utilizes biofeedstocks, such as dedicated energy crops, such as switchgrass, the use of forests or forest residues to produce energy, right, for heat production, liquid fuels, or electricity production. The CO2 that's produced when we burn this biomass is then captured using a carbon capture and sequestration system. And then the CO2 can be stored, as we indicated before, or utilized. BECCS has emerged as an extremely important component of strategies to hold temperatures to below 2 degrees Celsius. The Intergovernmental Panel on Climate Change's fifth assessment report in outlining the potential CDR approaches that could be used heavily relied on afforestation and reforestation, and then BECCS. So this is an extremely important one to look at. However, there are major challenges in terms of potential large-scale deployment of BECCS. And when I say large-scale, I mean moving from a few pilot plants, which is what we have currently, to sequestering 3 or 5 gigatons annually, for example, which is what some studies assume. First of all, is cost. Currently, the cost of sequestration utilizing this system would be somewhere between $130 to $175 per ton. So given the fact that the social cost of carbon is well below that, and the price of carbon on markets such as the European Union's emissions trading system or California's emissions trading system is well below this. Currently, there are not the incentives for large-scale voluntary uptake of this approach in the energy production industry. Now, as social costs of carbons increase, the regulatory bite increases, economies of scale potentially ensue. It's likely that these will become more competitive in the future, but for now, that remains extremely speculative. Another issue is potential public resistance to large-scale carbon sequestration. This program would require huge amounts of carbon to be transported from bioenergy facilities for storage, right? And this would be through trains or trucks or through pipelines. And then we would have to contemplate storing billions of tons of carbon dioxide underground, often in communities. And it's likely that we'd see substantial community resistance to this. You've all heard of NIMBY, not in my backyard. People say that this is NUMBY, not under my backyard. And indeed, in places like the Netherlands and Germany, where small-scale carbon capture and sequestration pilot plants have been planned, local communities have scuppered the establishment of those facilities on the grounds that they're afraid of the health and environmental impacts associated with carbon sequestration. So that'd be likely to slow the progress of this program and massively increase costs associated with litigation, if not downright eliminate the possibility of these projects being cited. There are also potential social justice and environmental issues associated with large-scale deployment of BECCS. Large-scale implementation of BECCS might require diversion of up to 1/3 of croplands to produce adequate feedstocks for a program that's scaled at 3 to 5 gigatons of sequestration a year. To put this in perspective, this would be 7 to 25% of net primary production, and would also probably require large swaths of forests and grasslands to provide adequate biofeedstocks. As a consequence, one recent study said it could result in increases of food prices for the world's most vulnerable peoples, those living on $1 to $2 a day in this world, by 30 to 40%. So it could have massive impacts in terms of caloric intake. It would also require huge amounts of water, primarily associated with creating huge plantations of trees to provide feedstock. One recent study concluded that it would require as much water as all the water that we currently use for irrigation on Earth, right? And this is a time with increasing populations and affluence are increasing water stress. Fertilizer needs would be huge. Even to sequester 3.5 gigatons, it would be equivalent to 15 to 75% of current global nitrogen fertilizer production. And it would likely push us over critical planetary boundaries. Also, biodiversity. A recent study indicated that based on the areas that would have to be cleared, including sensitive ecosystems, it would likely have a biodiversity impact that was equivalent to raising temperatures by about 2.8 degrees Celsius. So again, getting very close to a business as usual scenario. Okay, now let's move from the terrestrial to the ocean and look at an approach called ocean iron fertilization, or OIF. So the essence of understanding the concept of OIF is to understand the role of microscopic plants, phytoplankton, in the world's oceans and their role in sequestering carbon. So phytoplankton obtain energy through the process of photosynthesis. So they convert inorganic carbon dioxide from the oceans and convert it to organic carbon, which is stored in the organism's tissues. And indeed, about half of all the photosynthesis that occurs on Earth occurs in phytoplankton communities. Now, most of this organic carbon that's produced in this photosynthetic process is immediately consumed at the surface and converted back to CO2 and released into the atmosphere. However, a small portion of the remainder of the carbon is effectively removed from the system and transported to the deep ocean for storage when organisms, the phytoplankton organisms, die. And this is a process called the biological pump. And there's also some of this sequestration effectuated when fecal pellets fall to the sea floor. Proponents of ocean iron fertilization argue that phytoplankton populations are limited in certain regions of the world, and primarily this being the Southern Ocean, due to a deficiency in a critical micronutrient, and that micronutrient is iron. So they advocate introducing substantial amounts of dissolved iron, usually in the form of ferrous sulfates, in these areas to supplement natural supplies. They argue that this would stimulate phytoplankton growth and in turn ultimately increase carbon dioxide sequestration by essentially putting the biological pump on steroids. Early claims of purported effectiveness in terms of this approach were really fulsome. Some proponents of ocean iron fertilization claim that it could sequester as much as 25% of the world's carbon dioxide. It was also argued that it could be very cheap, maybe costing $2 to $5 per ton of carbon sequestered. However, this potential effectiveness is increasingly contested. This is one of the few carbon dioxide removal approaches where we've actually had field experiments to test it, and we've had 13 of them to date. Now, in most of these field experiments, we've seen fairly high proliferation of phytoplankton in patches of the ocean that have been fertilized with iron. That's the good news. However, drawdowns in the concentrations of atmospheric carbon dioxide will only occur if phytoplankton are sequestering substantial amounts of CO2 when they ultimately die and sink to the bottom of the ocean. However, this may not occur. Phytoplankton can be consumed at the ocean surface by zooplankton, the microscopic invertebrate species that feed on these phytoplankton. Zooplankton in turn can then be consumed by larger sea creatures, which can release CO2 back into the atmosphere by respiration and excretion. Also, much of the organic carbon is remineralized by bacteria back into organic carbonate and bicarbonate during the first 500 meters of sinking. As models of the potential for ocean iron fertilization have become more sophisticated, and we've taken into account this, the fact that proliferations of phytoplankton essentially create gigantic sushi bars in the world's oceans, the potential effectiveness of these approaches has started to decline. Only 3 of the 13 ocean iron fertilization experiments have demonstrated substantial sequestration of CO2 below the photic layer. One recent study concluded that at most, the technique could reduce atmospheric concentrations of CO2 by about 10%. Some more recent studies at Ohio University indicate that this may be about 5%. However, proponents argue that the jury is still out, that we need even larger experiments, longer in length to accurately ascertain the full extent of primary productivity. Moreover, they argue that even if it were only able to sequester 10% of the world's atmospheric carbon, for example, that it could be cobbled together with other CDR approaches in a portfolio approach that would ultimately effectuate the kind of sequestration that's necessary. There are also, however, potential negative ramifications of dumping iron into sensitive ecosystems. One issue that we have is that if you do effectuate large phytoplankton production, you don't get to pick and choose. It's not like Macy's. You get what you get. And one of the things that we're worried about is that there would be proliferation of phytoplankton species that would not be palatable by zooplankton species or production of toxic species. For example, in one of the ocean iron fertilization studies, the abundance and biomass of one phytoplankton species called Phaeocystis antarctica was increased substantially. This species proved unpalatable to mesozooplankton species in the region. And so if we had done this at a basin-wide scale, for example, it could have resulted in a massive biological trophic cascade. Ocean iron fertilization could also privilege fast-growing species of phytoplankton, including Pseudonychia, which produces domoic acid, a neurotoxin that can kill mammals and seabirds. Another issue, of course, is widespread eutrophication, that is proliferation of algae that can choke off light to species and create toxic algae blooms that kill species. We have examples of these toxic algae blooms in the Mediterranean and in the Black Sea, for example, in the 1990s that wreaked havoc with marine mammals in the area. And then finally, paradoxically, ocean iron fertilization could actually exacerbate climate change. The reason is that when phytoplankton begin to die and decay, it results in massive consumption of oxygen. And this can produce anoxic or oxygen-deprived dead zones. Beyond killing lots of species, these anoxic environments produce lots of methane and nitrous oxides, right, which are much more potent greenhouse gases than carbon dioxide. And so some studies say that this could offset most of the benefits of ocean iron fertilization, though we need additional research in this context. Okay, back to terrestrial options. And the next one that we look at, and this one is being widely discussed, and you've probably seen coverage of it in recent years, and it's called direct air capture, or DACS. DACS utilizes either the things you see on the left, we call these artificial trees, or the thing you see on the right, these gigantic filtration units. And it draws in ambient air and separates out the carbon dioxide for capture using chemical sorbents such as calcium hydroxide or amines. Direct air capture companies estimate that one of these artificial capture units here on the left would have the same physical footprint as a tree, but it could sequester thousands of times more carbon. And in theory, we could use direct air capture at a scale that would sequester enough carbon to return temperatures back to pre-industrial levels. But there's challenges associated with this approach. One is cost. A number of years ago, the American Physical Society estimated that DACS could cost somewhere between $600 to $1,000 per ton of carbon dioxide that's captured. However, a number of companies that are working on pilot projects now believe that they can bring the cost down to below $100 per ton. And quite frankly, if that turns out to be true, it could be a real game changer in terms of the competitiveness of this approach. And so it's definitely something to look at. Another challenge are energy needs. Uh, uh, it's uh, it's highly energy intensive. One recent study said that a large scale deployment of this technology could require a quarter of all global energy by 2100. Now, obviously, if you're producing that energy with fossil fuels, it's going to obviate a lot of the benefits of direct air capture. And if you're utilizing renewable energy, the question is if that is the most effective way to deploy renewable energy from a standpoint of climate policy. And that's something that's widely contested and being discussed in the climate community at this point. Another challenge is the same thing that we talked about with BECCS, which is sequestering billions of tons of carbon dioxide. You may have the same public resistance that we talked about before. There is discussion, for example, of trying to create a closed loop system of utilizing this carbon dioxide for more energy production and other uses. But many believe that the utilization of carbon dioxide, given the cost, is likely to be extremely limited. And so we are going to probably have to sequester billions of tons underground or in the world's oceans with all of the public resistance that may occur in this context. The last challenge is that this would be a massive industrial enterprise. It's been estimated that even sequestering 10% of atmospheric carbon versus DAX would require manufacturing about 10 million artificial trees. And these units would be the size of boxcars. So it's an ambitious prospect to do. All right. Next approach that we look at is called biochar. So biochar is charcoal produced from biomass, such as wood chips or agricultural byproducts or switchgrass, and it's produced via a process called pyrolysis, which involves superheating the biomass at temperatures of between 350 to 700 degrees Celsius in the absence of oxygen. Once biochar is produced, it can be spread on agricultural fields and the top layer of soil. And this can effectively store carbon in this biomass in a stable form for up to 1,000 years, compared to the much more evanescent storage of carbon dioxide that would otherwise occur in biomass. There's also lots of potential co-benefits, including studies that indicate that it could enhance soil moisture retention, increase crop yields, and reduce the bioavailability of heavy metals. But there's a number of issues associated with biochar. First of all, there's a wide range of potential estimates of sequestration potential, ranging from about 0.8 gigatons a year up to 9 gigatons a year. Some studies indicate that it might only reduce atmospheric concentrations of CO2 by about 10 to 50 parts per million. A lot of this contestation is associated with transportation costs of biochar, likely acceptance by farmers, incentives, and so forth. And we're in very early stages of working out that characterization. Moreover, while some biochar can be produced from waste, such as forest residues or municipal waste, large-scale deployment would likely require very large amounts of land to essentially create dedicated biomass that could be used in a biochar process. One recent study said that large-scale deployment could require as much as 3.9 million square miles of land. And so we have the same fears of that we talked about above in terms of BECCS and afforestation, in terms of displacement of small farmers on lands that might be required for biochar plantations. Also, potential trade-offs with other carbon dioxide removal approaches, such as BECCS or afforestation. And we'd have to figure out the optimal mix in this context. We also need a lot more characterization of biochar. Some studies show substantial storage of CO2 with biochar. Others show very little effect or actually show net increases in carbon release. Some studies show increases in the release of other greenhouse gases, such as methane and nitrous oxides, while some show that biochar would contribute to the stabilization of those for a longer period of time. Some studies conclude that application of biochar to soils could boost crop yields by up to 60%. Others show that it could diminish yields by up to 30%. A lot of this depends on the type of soil that biochar would be applied to, the climate that it would be utilized in, and the types of crops that it would be applied to. So as a consequence, we would need lots of close order sort of characterization, basically in a huge number of different sort of systems, and that would be extremely expensive at this point. Okay, we're going to look at one more approach now, and that's called enhanced mineral weathering. So chemical weathering is a natural process that continuously erodes away rocks in our landscapes. And in doing so, it sequesters virtually all of the atmospheric carbon dioxide over the course of millions of years. The way this works is atmospheric carbon dioxide dissolves in rainwater, and this forms a weak carbonic acid. When this precipitate strikes rocks, it helps to weather them. That is, it dissolves them and breaks them down. When silicate or carbonate minerals dissolve in this process, carbon dioxide is drawn into the solution from the atmosphere to form bicarbonate ions. Rainwater and these bicarbonate ions eventually end up in the world's oceans, where they're formed into carbonate minerals by calcifying organisms, which then sink out of the open surface and ultimately can effectuate the storage of carbon dioxide for 1,000 years or more. However, this is a very slow process. Currently, this natural weathering of silicate and carbonate rocks consumes about 0.25 gigatons of atmospheric carbon dioxide a year, which is about 3% of annual fossil fuel emissions. The idea behind enhanced mineral weathering is to massively accelerate the natural weathering process. It would involve pulverizing silicate rocks such as basalt or olivine to accelerate that process. This resulting powder would have a high reactive surface area that could be spread on large areas of agricultural land where plant roots and microbes in the soil would then speed up the chemical reactions and the uptake of carbon dioxide. It also could help us to address the twin brother of climate change associated with rising levels of carbon dioxide, which is ocean acidification, because it could enhance alkalinity in the world's oceans, ultimately in terms of this runoff.
Or you have to go out.
Some studies project that enhanced mineral weathering could ultimately sequester somewhere between 1 to 4.5 gigatons of carbon dioxide a year. But there's a number of challenges with this approach also. The mining process would require tremendous amounts of energy, which might be equivalent to about 10 to 30% of the amount of CO2 that's sequestered in terms of CO2 emissions associated with this energy process. It could be extremely costly. Some studies peg it up to $450 per ton of CO2, which means that it might ultimately only be able to be used in niche sectors where it's almost impossible to decarbonize through electrification or other processes. There's environmental health risks that might be associated with the releases of fine particulates that would be associated with this mining process. There's also potentially adverse biogeochemical impacts in oceans that would need to be assessed more thoroughly. The potential releases of things such as nickel or chromium associated with some of these minerals, and we're at extremely early stages of that kind of characterization, and the research again could be extremely expensive. All right, so with that in mind, the other question I want to look at is how might we govern this at both the international and the national level, given the fact that we see both a profound imperative to look at these options, but also acknowledging the fact that they could pose some serious risks, including in some cases in the global commons or in a transboundary context. So first of all, I want to look at the international regulation of these approaches. Now, to date, two regimes have sought to regulate carbon dioxide removal processes, largely in response to these ocean iron fertilization experiments that I talked about before. The first of these is something called the London Dumping Convention that was created in the 70s to address dumping of materials in the world's oceans that could imperil ecosystems. So in 2008, the parties to the London Dumping Convention passed a resolution on ocean fertilization experiments or ocean fertilization initiatives. And they established several conditions that the nationals of parties were supposed to comply with. First of all, it was to be limited to scientific research. Second of all, it could have no commercial motives. In other words, you couldn't be doing this to try to sell carbon credits on voluntary markets, for example, or regulated markets. And then third, it had to be subject to a risk assessment framework that was subsequently to be established by the parties. And indeed, in 2010, they established it. And here you can see the elements of environmental assessment that are supposed to be conducted before a permit is issued for an ocean iron fertilization experiment. Now, there are limitations to this approach in terms of regulating carbon dioxide removal. First of all, the resolutions that are passed under the London Dumping Convention are not legally binding on the parties, though they tend to be at least morally suasive in most circumstances. Second of all, you can only regulate a small sector of the CDR approaches that we talked about, those that are ocean-based and involve the placement of materials in the world's oceans. So obviously the London Convention would not be pertinent in terms of things such as BACs or direct air capture, probably not even enhanced mineral weathering. So some of the ocean-based approaches such as ocean liming, putting limestone in the world's oceans, right, to increase alkalinity and take up CO2 might be pertinent in the future, but it's limited. And third of all, this resolution was only focused on ocean iron fertilization, so it wouldn't be pertinent to even other ocean-based approaches, though presumably if we started research in that context or deployment, the parties to the London Convention might pass commensurate resolutions to regulate those approaches in the future. There's also a successor agreement to the London Convention called the London Protocol, and the parties to the London Protocol passed a resolution in 2013 that would amend the protocol that to regulate a broader swath of approaches. As you can see here, it refers to marine geoengineering activities. At the current time, the only one of these activities that would be regulated under that rubric would be ocean iron fertilization, but it's contemplated that it could be expanded to other things that would fall under the rubric of marine geoengineering, which it defines as large-scale interventions, including to seek to alter the climate, right? So that would encompass virtually any carbon dioxide removal approach that we're talking about. Now, this is significant because unlike the resolutions in the London Convention, this would be legally binding because it's an amendment to the convention itself. But it also has some limitations. First of all, it requires 33 countries to accept this amendment before it comes into legal force. And to date, only 5 parties to the protocol have adopted it. Second of all, some of the significant players in this area, including the United States, are not parties to the protocol, unlike the convention. And third of all, obviously, again, this is limited to ocean-based approaches. A second regime that's sought to establish some regulation over these approaches is the Convention on Biological Diversity, right, established in the 90s to address the biodiversity crisis in the world. They passed a resolution in 2010 that essentially establishes the same conditions as under the London Convention, only for the purposes of scientific research, no commercial motivation, subject to prior risk assessment. There's limitations to the CBD. Resolutions, again, are not legally binding. Many of the issues associated with CDR that we're concerned about, including human health implications, are not really encompassed in the mission of the CBD. And finally, not to put find a point on it, the CBD hasn't been particularly effective in even addressing biodiversity. So it's hard to believe that it's going to be effective in addressing this very esoteric topic, which will be extremely research heavy. But nonetheless, they have established a marker in terms of how they think this should proceed. Incidentally, some that oppose carbon dioxide removal have denominated this as a moratorium on carbon dioxide removal or geoengineering more generally. I think that's an overstatement. Essentially, what they've said is as in the absence of a governance framework and proof of the effectiveness of this approach and minimal negative impacts, they want to start with small-scale scientific research. But it does contemplate the possibility of an incremental movement toward accepting deployment of these technologies in the future. The last regime that I talk about that hasn't really talked about CDR, but seems like one of the more logical places in the future to address it, is the Paris Agreement. If we were to deploy these approaches, obviously we're doing it to try to address climate change. So it may be logical for Paris to take up CDR as a potential third response option in terms of climate change in parallel with traditional efforts to reduce emissions, as well as efforts to adapt to climate change. So one question is whether you could meet your nationally determined contributions or pledges under the Paris Agreement partially through CDR, right? So one thing you have to do is then look at Article 4.2, which talks about how one achieves one's NDCs. And it indicates that in doing so, parties are to pursue, quote, domestic mitigation measures, which with the aim of achieving the temperature targets of Paris. So the question is then, what our carbon dioxide removal approach is a mitigation measure. Now, while Paris uses the term mitigation 17 times, it never defines it, right? But its parent agreement, which is the framework convention, does. And in defining mitigation, it says these are efforts to either limit emissions of greenhouse gases or to protect and enhance sinks. And to the extent that we can construe carbon dioxide removal approaches as efforts to enhance sinks by taking in more CO2 and storing it, I think the parties could claim that this is a mitigation measure that they could incorporate into their NDCs. To date, the only one of the CDR approaches that have been expressly incorporated are afforestation and reforestation. But it's contemplated in the future that other approaches will also be encompassed. And so the Paris rulebook will necessarily have to be amended to provide for methodologies and standards of integrity and transparency to ensure that these approaches are reported accurately. And that's going to be a huge challenge. Paris Agreement also has provisions that might limit the scale and the use of some of these technologies. For example, the preamble indicates that when you take actions to address climate change, and clearly carbon dioxide removal would be one of those kinds of actions, you have to respect, promote, and consider obligations on human rights. Well, when we talk about BECS, for example, and the fact that it could massively raise food prices, that could negatively impact the human right to food. And so it might limit the extent that one could deploy this technology, and it certainly should be considered. If it massively decreased access to water, it could also violate the human right to water, for example, and so that would have to be taken into account. Of course, unchecked climate change could also massively undermine human rights. And so it would necessarily dictate a comparative risk assessment. And this language in Paris, even if it's in the preamble, which is not legally binding on the parties, may provide some guidance in doing that. And I think, as somebody who writes a lot on the ethics of these approaches, that clearly the parties should be thinking about that. Article 2 talks about enhancing the implementation of the convention in the context of sustainable development. Again, that could cut both ways. Some of these approaches, you can imagine, could have negative impacts in terms of sustainable development, but they could also help to contribute to sustainable development if they address unchecked climate change. And then finally, it talks about ensuring the integrity of ecosystems, including oceans. And so any of the ocean-based approaches that we've discussed could necessarily be scrutinized in this context also. And then finally, I'd say a lot of what will happen with carbon dioxide removal regulation will happen at the national level, especially for options that don't have a lot of transboundary impacts, such as direct air capture, for example. So some of the regulations that we could think of that would be pertinent include land use regulations, in terms of, creating huge plots of trees, for example, for afforestation or for BECS, clean water and air regulations for a lot of these approaches, including enhanced mineral weathering, as well as some of the forest-based approaches, as well as biochar. And then waste regulations. It's contemplated that for things like enhanced mineral weathering, we may use lots of things such as slag, for example, as a feedstock for the weathering process. But where we source that from and how it's regulated under waste standards would become terribly pertinent in that context. So in the longer term, it's likely if we start scaling these up, we'll start developing specific regulations for these processes. But in the shorter term, we're going to have to rely on current regulations and laws, many of which never contemplated the use of these technologies, and that'll prove to be a challenge. But it'll give lots of lawyers lots of work to do. So there's that. So I'm going to stop there and essentially say, I think that it is likely that these approaches are going to be increasingly discussed in society. If you look at the huge proliferation of corporate pledges in the last couple of years to achieve net zero by 2050, a lot of them include assumptions of large-scale use of carbon dioxide removal approaches, including a number that we've talked about here, planting of trees, BECS, enhanced mineral weathering. And a number of countries have started talking about this, including Switzerland and the UK, of the role of nets in meeting their goals. And so the questions of the integrity of those pledges, as well as some of the potential risks, and as well as the challenges of scaling up quickly to meet those, are likely to be abiding sort of considerations, especially for future generations. And with that, I'll conclude and open it for any questions that you might have.
Great. That was wonderful, Dr. Burns. If anyone has any questions that they'd like to ask, please feel free to take yourself off mute and go ahead and ask your questions.
I have a question. Can you hear me?
Yes.
Okay. Thank you for your presentation. It was very informative. I have a question about the governance strategies. Specifically, have you seen any governance strategies that talk about making sure that CDR is used to remove excess CO2 from the atmosphere instead of being used as a tool just to reduce emissions from fossil fuels or industrial processes? Because a lot of the things I've been starting to see, like big companies are starting to invest in CDR to reduce their emissions, but I think it's also important to realize that we have to remove the excess CO2 from the atmosphere as well, because even if we stopped emitting CO2 today, we still have tons of CO2 that are sitting in the atmosphere and causing global warming.
Mm-hmm. Yeah, it's a good question. There are some voluntary standards associated with CDR that are being developed, such as at Oxford, that talk about that, right? Essentially creating parallel sort of standards, right, and mandates. And some governments have talked about that also, but it's hard to know if politically if it will happen. One of the fears that we have is that we'll see the same thing that we saw under Kyoto, right, which is offsets essentially being misused, overclaims, and it providing a fig leaf for companies and countries not to structurally and aggressively decarbonize by hiding behind these pledges, right? And if that happens, it's unfortunate, because you're absolutely right. In order to meet the Paris Agreement's objectives, we're going to need both, massive decarbonization and the use of these approaches. And we're afraid of the moral hazard associated with these. We're afraid that it may effectuate carbon lock-in in some cases, which will make it much more expensive in the future to reduce emissions. We're also afraid that a lot of these claims will turn out to be chimerical, right? We talked about questions associated with permanence, for example, in terms of forestation and afforestation claims. And a lot of the pledges or a lot of the offsets that are being purchased in the markets now are in that sector, right? And I have serious reservations about whether those are going to occur. So you do have some people proposing that you essentially have both those tracks. People like Duncan McLaren, for example, at Lancaster, right, argues that you should have to make a pledge to optimize your reductions in emissions, and there'd be some kind of metric set up for that. And only then could you make any claims in terms of emissions reductions that would be effectuated through direct carbon dioxide removal projects or purchasing those kind of credits. But there's going to be a lot of political pressure to try to meet commitments utilizing this approach without establishing those kind of strictures. So we'll see what happens.
I have a question. Can you hear me?
Yes.
Okay. In reference to your discussion about replanting forests and planting 1 trillion trees and so forth, it's been known for quite a while that wetlands sequester carbon much more effectively, much more per acre of wetlands than per forests. And our wetlands are in pretty degraded state, both freshwater and coastal wetlands. And I'm wondering why there isn't a comparable program for creating and restoring and rehabilitating wetlands that could be more efficient at sequestering carbon and also probably less susceptible to fires?
Yeah, it's a good question. I don't know the answer to that. I mean, there is some discussion, right, of looking at the role of both peatlands and wetland systems in this context, right? And you're right. You get a lot more bang for the buck in this context. I don't know the answer to that. Clearly, we need to be looking at that more because there's lots of co-benefits. I mean, there's some co-benefits if you plant trees in the right areas too, but there's a lot of compelling co-benefits in terms of wetlands. I suspect a lot of it is again political. Our loss of wetlands are related to development in a lot of cases, and probably there's a lot of powerful forces that don't want to focus on preserving ecosystems that might get in the way of that kind of development. But that's just speculation on my part. It's expensive too. Restoration, wetland restoration can be extremely expensive, and you need a lot of characterization to do it correctly. That may be also a barrier, but it's clearly something we should be looking at in earnest.
Thank you.
I have a question as well. Thank you so much for the presentation.
Sure.
We talk about policies regarding those new technology in carbon removal. But at the same time, government has a role to encourage research and to learn more about those potential ways to eliminate carbon dioxide from our atmosphere and our society. As an undergraduate myself, many of those methods could have lasting implication on my future, whether they're implemented or not. Mm-hmm. So what advice would you give to the policymakers around the world in stepping on this line of encouraging research into this technology while also probing the risk at the same time?
Yeah, well, there's some good news in this context. If you'd asked me this question a year ago, I would have had to totally bemoan the incredible shortfalls of funding for research in this context, right? Which was incredibly de minimis. In the last year, at least in the United States, for example, there's been substantial increases in funding. In the latest round of the stimulus bill, for example, there's billions for research and development associated with carbon removal approaches, also carbon capture and storage, right, which is more focused on capturing it in the flue gas, right? So a different enterprise. It doesn't take carbon out of the atmosphere, but even that research can be pertinent for BECCS, right? So it serves a co-purpose. So that's good news. In Europe, there's more impetus for this also. In both Europe and the United States, there's increasing discussion of how CDR might be incorporated into the Green New Deals on both sides of the pond. But there's a lot of pushback in that context. You have a lot of NGOs that believe that this is kind of a get out of jail card for the fossil fuel industry, and so they have objections in that context. They're also worried about a lot of the social justice implications of large-scale tree planting in terms of land grabs. The same thing with BECCS and biochar to some degree, and they're worried about. They're less amenable to hard infrastructure sort of approaches such as direct air capture, for example. So those are issues that may slow down this kind of research. The characterization of risks, I think, is extremely important. You mentioned probing those risks. In my opinion, and I probably conveyed that in this presentation, hopefully, I think those can't be minimized. There's no free lunch at this point, right? We screwed this up. If we had started aggressively decarbonizing in 1980, when people like Jimmy Carter were talking about it and really meant it, we wouldn't be at this place where we have to start talking about large-scale deployment of speculative technologies, not only on this side, but on the other side of geoengineering, right? Solar radiation management, where we're talking about putting, 10 to 15 teragrams of sulfur dioxide into the stratosphere, right, to try to reflect sunlight away, or putting mirrors in space, right? We just wouldn't have gotten to that point, right? But we're there. We've expended about 75% of the carbon budget that remains to hold temperatures to below 2 degrees Celsius. We may blow through that budget by 2035, maybe even earlier. So because there are no free lunches, we have to look at technologies that may pose some serious risks. But having said that, I think we still need to adequately characterize them. We need to really acknowledge the risks and benefits and the trade-offs, and we need to try to minimize the impacts on the most vulnerable people in the world, right? The most vulnerable have already suffered from climate change. It would be tragic if the most vulnerable also are called upon to assume the most burden in terms of our responses, right? So that means, I think, that when it comes to things like tree planting, to try to minimize land grabs, we should be looking at doing it in developed countries where there's more regulations. Same thing with things like enhanced mineral weathering, for example, and mining operations associated with this. We need real public engagement. We need meaningful social license to operate to ensure that we adequately characterize these approaches and minimize their impact in terms of some of the vulnerable populations. That may or may not be incorporated into the kind of approaches that we're looking at, but we clearly need to be thinking about it.
Thank you very much.
Hi, Will. This is Alan Roebuck.
Hi, Alan.
I agree completely that geoengineering is also really scary. In fact, I'm leading a discussion in the Human Ecology Department next Wednesday on that here at Rutgers. But the overall picture is there is no way to suck the CO2 out of the atmosphere that we know of that's cheap and safe. So we have to do research. The National Academy of Sciences produced a report on designing new research programs over the next several years, and so that might be a way to do it. But wouldn't you say that a carbon tax, a gradually increasing carbon tax, would be a way to help both leave the fossil fuels in the ground and figure out how to live our life without emitting CO2? And if the price gets high enough, then direct air capture might become a solution or an idea if we can figure out where to put the carbon.
Oh yeah, it absolutely is. I mean, there's profound hypocrisy on the part of many who talk about now being woke when it comes to climate change, right? But saying we want this to be a market-based approach, right? I'd fulsomely embrace that, right? Because a market-based approach means that we're trying to capture the externalities that are associated with climate change and send market signals that optimize, adoption of alternatives and reduction of the use of products that have huge negative impacts. But to capture the externalities, you need things like carbon taxes, right? So I would say that the left should embrace the right's rhetoric in this context, but make sure that they really mean it. And the way to capture those externalities, probably in the most cost-effective and efficient way, is a carbon tax. More efficient than cap and trade programs, for example, and a lot of the proceeds, the revenue from, could either be rebated back to try to avoid regressiveness of those kind of taxes, right, for the most vulnerable, or some of that funding proceeds could be utilized for research and development in some of these approaches to try to achieve knowledge diffusion and economies of scale. So I absolutely agree. Now, it's a hard push because it's the T word, and there'll be lots of natural resistance. But you've even had people like the late George Shultz and the American Petroleum Institute who now say they're amenable to a carbon tax. Of course, you have to set it high enough to effectuate the kind of goals that you want. But it's good that there's at least some discussion of this across the ideological spectrum. So I agree with you, Alan.
There's
Hello,
a
Dr.
question in the, go ahead.
Oh, hello, Dr. Burns, and thank you very much for your talk.
Sure.
Of the technologies that you presented, are there any that you're particularly bullish about?
It's funny. I don't think I've ever done this talk without somebody asking that question, right? So I do have some thoughts in that context. With the caveat that I am a lawyer by training, right, and so don't want to get too over my skis in opining about these, right, and also saying that we're at too early a stage to pick winners and losers, right, in terms of research. I think one of the most promising is direct air capture. The reason is because it avoids a lot of the potential impacts on the global commons. Those are the kind of technologies I'm most squeamish about, both from an equity standpoint and from a legal standpoint, right, in terms of regulating them. And it potentially could be scaled up at a cost that could result in diffusion pretty quickly. I think the biggest challenges, though, with DACs that remain, again, are storage, right? Unless we really get good at carbon utilization, and I hope we do. I hope it can drive a green hydrogen economy, right? But I'm not sure right now we have a cost on carbon that would do that, right? But Alan's proposal, right, may be part of that too. And then we got to deal with the energy issue, right? Again, if we're going to use large amounts of renewables to run this system, is that the most judicious use of those renewables? Some people have started talking about the fact that there's excess renewable production at times when we can't totally utilize it in the grids, and we might be able to co-purpose this in a way that ensures that it's not an either-or proposition, right? Again, that's beyond my pay grade to know if we're capable of doing that, but it's certainly something that we should be looking at. So I would say direct air capture, but I'd say that in these cases, we're probably looking at an all of the above approach, right? Probably what we're ultimately going to have to do is cobble together a bunch of these approaches at a scale that's sustainable, but together get us to that range of 15 to 20 gigatons. Of course, that makes things more complicated in terms of governance and more costly in terms of deployment and all the characterization that I've talked about. But realistically, that's probably what we need. Whether we'll do that and do that in a time frame that's pertinent is a different question, of course.
Well, thank you everyone for joining, and thank you, Dr. Burns, for your wonderful presentation.
All right. Thank you, everyone. Have a great weekend now.